So today we shall be covering trigonometry, and the topic we'll be looking at is a little outside the standard syllabus, but we hope you will find it interesting. You may find it also useful for clubs and so on. And also some of the techniques will be useful for solving mathematics contests. We'll try to make it as accessible as possible. But if you have any questions in between, you feel free to jump in and ask. So I don't know whether we should give people two more minutes to join, and then we start, or we can start right away. What is the feeling from the group?
2 minutes or 5.
We give them. Okay, we'll just give them 2 minutes. What will happen is eventually we shall record the video, and we'll share with those who will not be able to make it, or those who will not make it on time. It's also in the evening, so it may be a good idea to get this out of the way as soon as possible. Maybe while we wait, also we can we can have some comments on how the previous lectures have gone, and if they have been useful at all. Can we have some comments? And if there's anything that we need to change? Okay. Are there any comments? Any reactions? No. Oh, let's see. Oh yeah, I can see a comment here. The previous lectures have been great. It would be nice to have feedback. So if you have some feedback, feel free to. Yes, I will share the slides as well. I didn't share the ones for the previous talk, but I will put everything together and share slides so that they can be available. So I think we can proceed. I'll share my screen, and maybe someone can confirm if you can see the slides.
Yes.
Good. So we will recall from the previous class we encountered some identities. There's this cos squared theta plus sine squared theta is equal to 1. That's a Pythagorean identity. And then there are these others which we were able to figure out from the graphs. By just looking at the graph, these two identities can be observed, and this as well. These last ones. These ones were, it was possible to just check that using the graph and also the construction of the functions using the unit circle. So we will be using these to come up with some new identities, as you shall see. So another thing we need to use to recall is the formula for computing the sine, cosine, and tangent. The opposite of a hypotenuse for the sine, adjacent of a hypotenuse for the cosine, and opposite of adjacent for the tan, although the tan can also be given as the sine over the cosine. So the first set of identities we shall look at are called the compound angle identities. So sometimes it's necessary to express ratios of sums of angles or a difference of two angles in terms of the ratios of the individual angles separately. And this is the aim for this particular section. So the aim is to figure out how we can do that. Just hold on. There's something I need to set up here. Good. Now we can proceed. So we will consider the case where theta, these two angles, theta and phi, are both acute, and their sum is also acute. So we shall use this diagram to work out our identities. So if you look at this angle, the angle from, say, this angle, let's call it ROP. The angle ROP is the sum of these two angles, theta and phi. So we want to find the sine of the sum of these two angles. If we can, this diagram, we have two right angle triangles. We have OPQ and we have OQR. So we shall be using the formulas for the sine and cosine as we go along. So the sine of this, also we have dropped a perpendicular from this vertex to this to the side OP, and it meets the side OP at N. So this is a perpendicular. So that again we have this triangle ONR is also a right angled triangle. So now we can use the formula for the sine. The formula for the sine is the opposite of a hypotenuse, so that should be NR over OR. If you consider this right angle triangle, ONR. Now this length, NR, can be split into two. We can split it into this length from from N to S and S to R. But NS is just the same length as PQ. So we can replace NS with PQ so that we have this as PQ plus SR over QR. And we can separate them so that we have PQ over OR plus SR over OR. So we multiply each of these terms by 1. So we multiply PQ over OR by OQ over OQ. So we're basically multiplying this by 1, but we choose a very convenient one that will help us progress. And we also multiply this SR OR by 1 again, which is QR over QR. So when we rearrange this, we have, this can now be rearranged as PQ over OQ, but PQ over OQ is just the sine of theta. So if you check, the sine of theta is PQ over the hypotenuse, and OQ over OR is the cosine of phi, and so on. SR over QR is the cosine of theta, and QR over OR is the sine of phi. So now we've been able to write the sine of the sum of these two angles, theta plus phi, as sine theta cos phi plus cos theta sine phi. So this is our first compound angle identity. So with just this one, we can derive all the remaining ones by using the previous properties and identities that we have looked at. So if we replace the angle phi by negative phi, then this is what we end up with, sine theta minus phi. And we use the same formula from the previous. We just use this same formula, sine theta cos phi, but now we replace phi with minus phi on both sides, in both terms of the right-hand side. That's what we have done here. And we remember that the cosine of negative phi is just the same as the cosine of phi. And the sine of negative phi is the negative of sine phi, so that this now becomes negative. Now we have a second compound angle identity, where we get the sine of the difference of two angles. So for the next identities which involve the cosine, we shall make use of these two identities. So using this first identity, the cosine of theta plus phi is the same as the sine of pi over 2 minus theta plus phi, which can be rearranged to pi over 2 minus theta minus phi. Now you can use the previous formula for the sine, the compound angle formula for the sine function, and expand this, and this is what we'll obtain. And remember that sine of pi over 2 minus theta is just the cosine of theta, and the cosine of pi over 2 minus theta, again, is just the sine of theta. So we end up with this formula, and this gives us our third compound angle identity. So if by all means, feel free to stop and ask questions along the way if there's anything that is not clear. So again, in this identity that we have here, we can replace phi by minus phi, and then we'll end up with the cosine of theta minus theta plus minus phi. And then we just apply the previous formula for the cosine. And this is what we end up with: cosine of theta, cosine of phi plus sine of theta, sine of pi. And this gives us our fourth compound angle identity. So now we have a total of 4 compound angle identities that we can use. Now we can also get the compound angle identities that involve the tangent, or rather the tan. We already know how to get the compound angle identities for sine theta plus phi and cos theta plus phi. So we just use them here. And if we divide the numerator and the denominator by this cos theta cos phi, this term here, it simplifies. The top term will simplify to sine theta over cos theta plus sine phi over cos phi. And the bottom, the denominator will simplify to 1 minus sine theta over cos theta, sine phi over cos phi, which now simplifies to tan theta plus tan phi over 1 minus tan theta tan phi. So this gives us the first compound angle identity involving the tan. And in total, it is the 5th one. We can also get the 6th one by just replacing phi with minus phi again. And this is what we get. We have tan theta minus tan phi over 1 plus tan theta tan phi. So it's difficult to remember all this, but I will share the notes so that you can look at them later, and the video will also be available. So in any case, wherever we shall be required to use these identities, we shall write them out, or we will simply recall them. Now, based on those compound angle identities, we can come up with a double angle identities. This is a case where theta is equal to phi. So we can get sine 2 theta. It will simply be will be twice the sine of theta and the cosine of theta. And the cosine of 2 theta turns out to be the cosine squared theta minus the sine squared of theta. And the tan of 2 theta. So all this is just application of the compound angle identities where theta is equal to phi. So tan 2 theta turns out to be 2 tan theta over 1 minus tan squared theta. So again, these are very useful identities, and they are just derived from the compound angle identities. So there are two more ways you can write the cosine of 2 theta if you make use of this Pythagorean identity. So from the compound double angle identity, we know that the cosine of 2 theta is cos squared minus sine squared theta. So we can replace sine squared theta with 1 minus cosine squared theta, and it simplifies, the whole thing simplifies to 2 cos squared theta minus 1. So there's also one more way. You could replace cosine squared theta with 1 minus sine squared theta, so that you get cosine of 2 theta is equal to 1 minus 2 sine squared theta. So the two identities for the cosine of 2 theta are here at the bottom. So that gives us, I think, 3 ways to write the cosine of 2 theta. The previous one was, the previous one was here. The previous one is cos squared theta minus sine squared theta. And then the other two are these 2 cos squared theta minus 1 and 1 minus 2 sine squared theta. So depending on the situation, it may be more prudent to use one form of the identity compared to the other. So now we now move on to the half angle identities. So we know that the tan of 2 theta is given by this formula, 2 tan theta over 1 minus tan squared theta. So if we use the double angle identities and this Pythagorean identity, we know that the sine of 2 theta is the same as 2 cos theta sine theta. So we divide by 1 because cosine squared plus sine squared theta is just 1. So we divide this by 1. And then after we divide it by 1, we divide the numerator, both the numerator and the denominator, by the cosine squared of theta. And this is what we end up with. After simplification, this becomes 2 sine theta over cos theta, 1 plus sine squared theta over cosine squared theta, which simplifies further to 2 tan theta over 1 plus tan squared theta. So the reason it's called the half angle identity is the angle that is used on this end is half of the angle here. So you can see theta is half of the angle that appears here. The same with the tan. Theta here is half of the angle that appears here. So in the same fashion, we can use the double angle. Yes, Collins, you have a question?
Yes, Dr.
Yes.
In the previous slide.
Yes.
Yes, you have said that we divide the denominator by 1. Can you explain where we are getting this 1 plus sine square theta and cos square theta?
You mean this one at the bottom?
Yes, yes.
We are using this identity. this identity says that the cosine squared of theta plus the sine squared of theta will always be equal to 1.
Mm-hmm.
Yes. So if anywhere I put this, it's the same as putting 1. So this is 1. Cos squared theta plus sine squared theta is identically equal to 1. It's always equal to 1. So if I divide by this, it's the same as dividing by 1. Is that making sense?
Yes, yes.
Your question is answered, I think.
Okay.
Or we can move on. So we do the same for the cosine of 2 theta. If you apply the double angle formula, you have cos squared theta minus sine squared theta. Then we divide by 1. And again, divide both the numerator and the denominator by the cosine squared of theta. And as you can see, it will simplify to 1 minus tan squared theta over 1 plus tan squared theta. So we have been able to write all the three. You see the sign, we have a tan of 2 theta. We've been able to write it in terms of tan theta. The same with sine of 2 theta. We're able to write it in terms of a tan of theta. And we can see in the last one here also, the cosine of 2 theta, we're able to write it again in terms of tan theta. So all the three can be written in terms of tan theta. And these are what we call the half angle identities. So to put it in a more formal way, if we set this angle 2 theta to be equal to phi, then tan of theta will just be tan of phi over 2. And we choose to call it t for simplicity. And if we do that, then we can rewrite our identities in this form so that every tan of phi is the same as 2t over 1 minus t squared. The sine of phi is the same as 2t over 1 plus t squared. The cosine of phi is the same as 1 minus t squared over 1 plus t squared. So these are the famous half angle identities. They're called half angle because what the angle that appears in the right hand side of the equation identity is half of the angle that is on the left hand side. So this is a convenient way of writing this, as long as you keep in mind that t is tan of phi over 2. I hope that is making sense. So there we are with the half angle identities. So we can move on to the factor formula. So here we consider the compound angle identities again. So sine of theta plus phi and sine of theta minus phi. So we perform some operations on this. If we add the two equations, this left-hand side will become sine of theta plus phi, brackets, plus sine of theta minus phi. And when we add these terms on the right-hand side, we can see that this term on this last term will vanish because you have cos theta plus sine phi. If you add to negative cos theta sine phi, you get 0. So the only term that survives is this, and it appears twice: sine theta cos phi and sine theta cos phi. So we add them, we have 2 sine theta cos phi. Okay, so this gives us this is one of our factor formulas. So if we subtract these two, we subtract this second equation from the first, then what happens here is something changes now again. Here it's a sine theta and cos phi, which will disappear.
Oh.
Is there a question? Oh, okay. So on this side, the only term that will survive will be sine theta cos phi. Sorry, it will be cos theta sine phi, and there'll be 2 of them. So 2 cos theta sine phi And then on this side, we simply subtract the 2, like that. So now we can go a step further. If we set up these two simultaneous equations in theta and phi and solve them, then we can write theta as a half of alpha plus beta and phi as a half of alpha minus beta. If you'd like to convince yourself that this is true, try to solve this system or this system in 2 variables. Just hold on. There you go. So try to convince yourself that this is true. If you solve this system, you'll get theta is equal to a half alpha plus beta, and phi will be equal to a half alpha minus beta. Okay. So I think we're all in agreement that that is true. So if with that in mind, now we can write this equation that we had. Now we can be written as follows. You just replace theta with a half alpha plus beta and replace phi with half alpha minus beta. Is someone who will not? Okay, it's quiet now. I don't know where the noise was coming from. So
yeah, make me a co-host. I can try to help you with this.
I'll just let me find you. Okay, now you are co-host. So we have this identity that we set up in the previous part. So if we replace theta by half alpha plus beta and phi by a half alpha minus beta, it simplifies to this: sine alpha plus sine beta. That is for this right-hand side will be equal to 2 sine alpha plus beta over 2 cos alpha minus beta over 2. So this form is a final form now we have of a factor formula for sine alpha plus sine beta. So we can do the same for this second equation, and we have sine alpha minus sine beta will be 2 cos alpha plus beta over 2 sine alpha minus beta over 2. So the process is just the same as what we did up here. We use theta, we take theta to be a half alpha plus beta and phi to be a half alpha minus beta, and we put those into this equation, and we'll end up with this second factor formula. So using the same ideas, we consider these two identities again, the compound angle identities. And proceeding in a similar fashion as before, using the same ideas, we end up with cos alpha plus cos beta is equal to 2 cos alpha plus beta over 2, cos alpha minus beta over 2. And cos alpha minus cos beta will be negative. Here you have a negative, 2 sine alpha plus beta over 2, sine alpha minus beta over 2. So this gives us a second set of the factor formulas. So I think that that completes the set of identities that we wanted to derive today. If you have any questions before we go to the examples, you can ask now. Okay. So we will now move to solve a few examples, and then we will stop after we solve the examples. So the first example we look at is given that the sine of alpha is equal to 3/5 the cosine of beta is -4/5, where alpha is an angle between 0 and pi/2, and beta is between 0 and pi. Without using a calculator or tables, find the values of the following: the sine of alpha plus beta, the cosine of beta minus alpha, and the tan of alpha plus beta. So the interesting thing about this is you can do this without having to know what the angles actually are. Because of the formulas that we have, we don't need to know the angles. We can actually work out these values. So using the identities, we can find the cosine of alpha. Remember, the cosine squared of alpha plus sine squared of alpha is equal to 1. And you can rewrite this as the cosine of alpha is equal to the square root of 1 minus sine squared of alpha. And that works out to 4/5. And the sine of beta works out to be 3/5. It's the same as the square root of 1 minus the cosine squared of beta. So if you use this compound angle formula, then we easily get our value. I think the rest can be easily worked out. I seem to have left out the working out. We have worked out the cosine of alpha, and we have worked out the sine of beta. So the sine of alpha is easy to work out also. It's it's given. Sorry, I think it's given in the problem, right? Sine of alpha and cosine of beta are given in the problem, so we don't need to work them out. So we just plug them into this formula, and we get that the sine of alpha plus beta will be equal to 0. So again, here we don't need to know what alpha and beta are, but because of the formulas, we're able to work this out. Now the next one is to find the cosine of beta minus alpha. Again, we use this compound angle identity, and then we just plug in the values, and we find that the cosine of beta minus alpha is -7/25. It may be useful to also compute this where you are, so that in case there's an error, you can point it out. That can happen. When solving this, sometimes it's possible to make some errors. And the last one is tan. We know that the tan of alpha will be 3/4, and tan of beta will be -3/4. Here you can simply use the formula that the tan of alpha is the same as sine of alpha over cosine of alpha, and the tan of beta is the same as sine of beta over the cosine of beta. And this turns out to be 0 again. And also, one other way to do this was to just write this as tan of alpha plus beta is the same as sine of alpha plus beta, which you already found to be 0, divided by the cosine of alpha plus beta. So eventually, you still get 0. This is a little stretched out because we just wanted to use this formula, but you can solve it faster by just using the previous two formulas. So let's see if we can, if there is no question on that, we can move on to the next example. So without using a calculator or table, find the values of the following in sad form. So we can work out the sine of 75 by using the set square angles, 45 degrees and 30 degrees. And using the compound angle formula and plugging in the values. And when you rationalize the denominator, I think this is what we should get. You can also double check this to see if the computation is correct. So we've just left the answer in sad form. This, I think, is a mistake. This should be cosine. It should be cosine of 75 degrees. So we use the compound angle formula for the sum of two angles, the cosine of a sum of two angles. And this is what we get again as the cosine. I mean, this should be the cosine of 75, not the sine. So this should be the cosine of 75 degrees. Okay. And the tan, again, you can just get the sine of 75 over the cosine of 75, and it simplifies to 2 plus root 3. You can do this by rationalizing the denominator, and you'll end up with 2 plus root 3. I left out the details, but now you can try to convince yourself that these two are actually equal, and the same for A and B. So here we are going to use the identities to prove this one, that the sine of theta is equal to 3 sine theta minus 4 sine cubed theta. So the solution, we make use of the compound angle formula. We split 3 theta into 2 theta plus theta, then apply the compound angle formula here to obtain this expression. Now, if you can apply the double angle formula on sine 2 theta and cosine of 2 theta to obtain this next expression. And it simplifies to 2 sine squared theta cosine squared theta plus sine theta minus 2 sine cubed theta. But if you look at the problem, it requires us to have everything in terms of the sine. So we write cosine squared theta in terms of sine, a sine function, and we have the next step here, so that cos squared theta is the same as 1 minus sine squared theta. And all this will simplify to 2 sine theta minus 2 sine cubed theta, if you remove the brackets there, and plus sine theta minus 2 sine cubed theta. And it simplifies to 3 sine theta minus 4 sine cubed theta, which is exactly what we wanted to show. So by making use of the compound angle and the double angle identities, we've been able to prove this. So here we have some two, what we call parametric equations, and sometimes this can happen and we may be required to write an equivalent equation, which is just in terms of x and y, or if you like, you can call it the rectangular form of these parametric equations. So let's see how we can do that. We know that the secant of theta is the same as 1 over the cosine of theta, and this is equal to y. So this means that the cosine of theta is the same as 1 over y. That's the first step. We also know that the cosine of 2 theta can be written as 2 cos squared theta minus 1. So we picked this one because we already have cos theta here. So this seems to be the more appropriate identity to use. So here we have x is equal to cos 2 theta, and cos theta is the same as 1 over y. So if I replace 1 over y here, I end up with x is equal to 2 times 1 over y squared minus 1. And after a bit of algebraic manipulation, it simplifies to this: x plus 1 in brackets, y squared is equal to 2. Again, you can convince yourself that this is true before we move on. Let's look at another example. So So here is another example. We are supposed to show that the cosine of theta plus the sine of theta minus 1 divided by the cosine of theta minus the sine of theta plus 1 is equal to a tan of half theta. So let's see how we can do this. So here we make use of the half angle identities. If we set t to be the tan of theta over 2, then we can write the cosine of theta as 1 minus t squared over 1 plus t squared. The sine of theta will be 2t over 1 plus t squared. Again, here we're just using the half angle formulas and minus 1. We also use the same half angle formulas at the bottom. Now, if you multiply both the numerator and the denominator by 1 plus t squared, it simplifies to this. And putting the like terms together, you end up with this expression 2t minus 2t squared over 2 minus 2t. And after some manipulation, we end up with this. 1 minus t and 1 minus t will go, so that we are left with, and 2 will go with 2 as well. So that we'll be left with only t, and t is exactly tan of theta over 2, which is what we had. And that is exactly what we want to show. So again, here we have just made use of the half angle formulas to prove this, this equation. Let's see if we can do one more. So here we have an example which says show that the sine theta plus 2 sine theta plus sine 5 theta divided by the sine of theta plus 2 sine 5 theta plus the sine of 7 theta is equal to sine of 3 theta plus 5 theta. So this, we make use of the factor formula. And when we use that, we get that the sine of theta plus the sine of 5 theta is equal to 2 sine 3 theta. So 3 theta is the same as theta plus 5 theta over 2. So that is 6 theta over 2 will give you 3 theta. And theta minus 5 theta is equal to minus 4 theta over 2 is minus 2 theta. But the cosine of minus theta is the same as the cosine of theta, so this can just be left as 2 theta. We also have a sine of 3 theta plus a sine of 7 theta is equal to 2 times the sine of 5 theta plus the cosine of 2 theta. So this one simply picks part of, this first one simply picks this first and the last term of the numerator. And this one simply picks the first and the third term of the numerator. So when we do that, we don't do anything to these middle terms, because after we use the factor formula, we have some advantage here. In the top here, sine theta is common, sine 3 theta is common, and at the bottom, sine 5 theta is common. So we can actually pull them out so that we have 2 sine 3 theta, and in brackets cos 2 theta plus 1. And here we have 2 sine 5 theta in brackets cosine of 2 theta plus 1. These two will go, they cancel out, and we're left with sine of 3 theta over sine of 5 theta, which is exactly what we wanted to show. So here we have made use of one of the factor formulas, and this is what we wanted to show. And we've been able to show it. I don't know if there are any questions on this. Can you hear me?
Yes.
Oh, good. The place was a bit too quiet. So that was all for today. What follows is just the tables with the identities. Put them in tables. And if you like, you can attempt some problems. There are some 2 problems for you here. So the floor is open for any questions from the talk. Any questions? So or any comments, if you have any comments, if you feel there's something, there's more we could have done in trigonometry, but given that we have only 1 hour, I had to shorten this. There's more we can do on triangles, the cosine rules and the sine rules, and so on. I don't know if we should continue with trigonometry for the next talk, or if you have any other preferred topic. For the target is usually high school, though this talk was a little beyond the high school curriculum. So this one was a little beyond the high school curriculum, but it's things that high school students can also understand, and they're useful to know because especially if you if you go to do a science-based course that involves some mathematics, you will find this useful at the university. It will it's things you can understand now, and you will still find them useful later. So I'm waiting for any comments or questions. So maybe how do we get your email? There's someone who wants the video and not sent to the email. How do we get your email? You can. Okay, yeah. So there's a suggestion that I complete the slides on the remaining parts, the cosine and sine rules, and then we share with the rest. But other than that, is it possible to get some suggestions on the topic that you would like us to cover next? Or even some comment on whether this was helpful?
Yeah, are we able to do it with calculus or maybe algebra?
To do what with calculus?
Like having a session like this with calculus or algebra being discussed.
Okay, so the target is usually high school, so we normally try to find topics that can cover can be understood by the high school students. So if we go into calculus sometimes involves concepts that are foreign to high school students. So that becomes a bit of a problem. So if you can suggest topics that will cut across both. I know we have some students from the university participating as well, so we will try to make it useful to them, but we want topics that can cut across both high school and campus. Yes, Omondi, you are raising your hand. You need to put on your microphone.
James, I think if they agree next time, I can take them through inequalities. Yeah.
So we have a suggestion for inequalities. Yes, Omondi. Omondi, please.
Angle properties of circles.
Angle properties.
Yeah. Please.
Okay. So some of them, even if you're not able to make a video, we can prepare slides and share.
Yeah.
So basically, you're talking about geometry.
Yeah.
Yeah, you want geometry covered. Any other suggestions? We would like to make this more useful to the listeners. So good if we can get ideas from the listeners.
Actually, I think I support if we are able to, you are able to tackle the linear inequalities.
The inequalities. So I think we can put those in line. So we have linear inequalities, and then we have the geometry. We can start with the linear inequalities in the next 2 weeks, and then after that we will do some geometry. Is that acceptable?
Yes.
Okay.
Okay. So for next week we shall have Dr. Ongaro presenting the inequalities. So if you want to we have a Facebook page. If you would like to follow, we shall post the link to the video on that Facebook page. I'll just put the name of the Facebook page in the chat so that if you'd like to check on that, you can. So I'm putting that on the chat, the name of the Facebook page. We will also be putting a link to the video on the Facebook page. So in case you need to, and also the previous, I should give you a link of the YouTube link to the previous videos. If you wish to watch the previous videos as well, we have them on YouTube. Let me try to get them now. This is Dr. James Katende. I'm from the School of Mathematics. So I'll just post the link to the video from the previous, where is the chat here? So there, I've posted the link to the video for the previous class that we had. So I think we are in agreement.
Post it on YouTube or on the chat?
No, that's for the previous. I've posted the link to the YouTube video in the chat for the previous class, the one we had 2 weeks ago. This one I have not put it on YouTube yet.
I'm saying I don't seem to see it on the chat.
Oh, just hold
Maybe
on.
you sent to someone privately.
Oh yeah, I think I didn't realize. Let me change this. Should go to everyone. It's not changing. For some reason, everyone. Yeah, now it has agreed. So there, I had sent to, looks like I'd replied to a message in particular and sent it to someone. So now it is in the public. You can see it?
Yeah.
Okay. If there are no further questions, I think we can stop there. And we can wish everyone a good evening. We meet again in 2 weeks. You will, Dr. Ongaro will be talking about the inequalities. Yes, Charles, you have some comments?
Just to say good evening to everyone, and thanks for being there.
Yes.
As we continue the training, it's great. I think, Daktari, the PowerPoint in those angle properties, we should visit it next time when we're having a session on properties.
Oh, okay.
I think it's usually the easier part for high school students.
Yes.
And I guess it should be very interesting for them.
Okay. So I think after inequalities, we shall move to geometry then. So
yeah.
Some of those properties. Yeah, this is good. At least we are getting some feedback on which direction to go. So thank you very much for attending the class. We shall share the video as soon as I process it. And then we meet again in 2 weeks. We will be talking about inequalities. Thank you very much, and have a good evening.
Same.
Thank you.
Thank you.
Thank you.